is a source of variability that starts with the sun's light and the solar wind coming off the sun, that when it carries its magnetic field into the domain of Earth, it can interact with the Earth's magnetic field, and that is the source of much of the space weather that happens that we're going to be talking about. Space weather was essentially discovered for the first time in 1859 when Richard Carrington and Richard Hodgson were independently looking at something, and they saw something that nobody had ever seen before, which was the signature of a flare on the sun and the subsequent geomagnetic disturbance. Nowadays, of course, in these beautiful pictures that we can see from the International Space Station, we can readily observe the phenomena, many of the phenomena associated with space weather, and we can immediately sense the magnitude of the geographic extent of space weather. It really is a globe-spanning phenomenon. It spans multiple continents and many countries, which is why an international setting and an international attack on this particular phenomenon, set of phenomena, is so important. We've seen a tremendous growth in the interest in space weather. And in the blue diagram in the background, all I did was search Google for, search the astrophysics data system for publications related to space weather. And although there are many more publications that ADS does not probe for this, you can see that there's a very rapid growth over the last decade. Even more rapid is what you find if you look at Google and ask for space weather pages. You can actually specify a year on which pages like that would appear. That's the red curve that shows an even faster growth. It hits over 130,000 individual websites, web pages in the last year. That growth is mimicked by the growth in the customer base. Like, for example, NOAA's Space Weather Prediction Center sends out alerts and email messages to subscribers. The blue curve on the right-hand side is the growth rate in that. It peaked over 40,000 subscribers, and those are not just individuals, those are entire corporations, entire organizations that are interested in space weather. Matching that, of course, is if you ask for space weather forecasts, you get a mile 31,000 sites that have that set of words in it. So finding your way through it is difficult, but if you look through them, and the large ones, they're sort of in order in which Google returned them, you will see that there are forecast sites from all the official organizations that we are representing or work with in this environment that readily show up. Now, where does the source of all that space weather lie? Well, I'm not going to talk about the dynamo deep inside the sun or the dynamo deep inside the Earth, but basically the sun sends three things our way. The first is the one we are most familiar with, visible light, the magnetized wind that I already mentioned, and energetic particles. Ordinary material moving at near light speed can do bad things. These are all variable. The sun's light output may vary by a tiny 0.1%, and it's an important variation, but not very big. But once we look at the extreme ultraviolet and X-rays, the entire sun can brighten by a factor of 1,000 or 10,000 in a matter of minutes. The variable solar wind may change its wind speed by maybe a factor of 3 or 4 or 5 if you're really looking at the extremes between the slowest and the fastest wind. But what really varies, and is most important for space weather, is the content of the magnetic field in it, and particularly the orientation of the magnetic field. And the energetic particles coming from solar flares and interplanetary shock environments and the consequences of those in geospace, of course, vary by very large numbers. Now, these three different pathways come back a number of times in my presentation because each of them has its own set of consequences that we call space weather. We can talk about satellite drag and radio blackouts as a response of the Earth's atmosphere to the light input from the sun. The aurora, a pretty spectacle, but that are signatures of what happens in the magnetospheric field that couple into the geomagnetic field. And of course, energetic particles are dangerous to whatever is up in space or high in the Earth's atmosphere. I'll come back to that in just a moment. So you see these three different pathways come back a number of times. We live in a really remarkable time in that we have wonderful observational coverage. This is just one example of it, where we can trace phenomena from the left, from the right on the screen to the left, with a set of instruments, in this case from the stereo spacecraft, when they leave the sun, move through the heliosphere and impact geospace, directly observable in imaging. It's harder when we're talking about the magnetic fields moving through the heliosphere. Magnetic fields are the thing that really drive all that variability, and one of the prettiest manifestations of that, I think, we can see in the solar atmosphere. If we tune into a particular line of a spectral line of hydrogen, we get images like this, where we can see these linear striations that are the signature directly of the magnetic field. Now, these are very hard to obtain. These are observations that, if I put the Earth to scale, you might say, well, you're a long way off the physical scale, which is, of course, one of the main problems that we are tackling, not just on the Sun, but in anything related to space weather. But if we look at it on the scale of the Sun, that little blue box is the entire field of view. And I don't know about your favorite currencies, so I've not assigned a currency, but there's bound to be a 10-cent coin somewhere. If you put a 10-cent coin 10 miles away, that's the resolution of this kind of imagery. These can be taken from the ground, but they are literally 1 in a million image sets. They're very hard to take, require advanced instrumentation and a great team to assemble. Doing things from space is a little easier, but tends to be a lot more expensive. Moving those perturbations that become space weather through the heliosphere is hard to observe, other than by scattered light, of which I just showed you an example, but we can do a lot of that in the computer. But it's easier to compute hydrodynamically than magnetohydrodynamically, and that's a leap forward that we still have to make. And then, of course, you realize immediately, that you see as you zoom in on this picture, there's this great nesting of scales from the very vast heliosphere as a whole to the tiny Earth. But even the tiny Earth has a lot of scales behind it if we have to understand what happens in the magnetospheric field. That modeling is also becoming more powerful, where we can see the magnetic field of the Earth reshaping, subject to its internal instabilities and subject to the solar wind driving, with all the reconnection that happens that drives flows in different directions. This is just showing you part of the power of visualization and also the problems of visualizing this three-dimensional world. And then we have to take, because we're talking about space weather, it has societal impacts, we have to take that into our technological infrastructure. Here's an example of the European high-voltage electric power grid, and the big blue and orange bubbles show you where the electrical currents run into and out of that grid, just before there was a major power interruption in southern Sweden. This is largely modeling, but there is a lot of information upon which that modeling is based. We can do the same for other continents. Here's an example of a series of measurements taken in the United States. All these bubbles are where the USGS, the United States Geological Survey, has its ground stations, and the size of the bubble essentially gives you a measure of maximum rate of change on a given day in the Earth's magnetic field. And then there are these black boxes that show up. The black boxes are wherever there is a major disturbance in that high voltage power grid. And you see two things immediately. First, these bubbles are sort of in step, but not entirely. There is fine structure in the way that the Earth responds, the Earth's magnetic field responds. And on top of that, there's more complication if we're talking about the electric field, because then you have to fold in Earth conductivities and penetration depths and skin depth effects, etc. And then the grid does not have to fail when there is large geomagnetic variability, but something might happen. So we hunt through this and try to find correlations from which to learn what types of space weather are most effective when we're talking about our societal infrastructure. And in order to do that, we have to understand that entire web of connections. And I'm not going to read them even to you. There's a lot of steps to be taken to understand space weather. With the growing interests of space weather, there's also, that is basically driven by a growing concern. And this is just one image out of a study that we did, polling those 35,000 at the time we did this, customers of the US Space Weather Prediction Center. And we looked at all these different sectors in society, and you can read them on the right-hand side. They basically go all the way from agriculture to transportation services and every one of their alphabetical partners inside here. And we asked them, how concerned are you about consequences of a major geomagnetic storm? And most of this diagram turns out to be colored. Colored means there is a concern that there's a moderate impact of 80% among 80% of these customers, but it's really about 60%, more than the right-hand half of this diagram is orange, and I guess it shows up as purple on my screen, brownish on that screen, it should have been red, where people are really concerned that there could be major consequences. So there are major consequences expected, not just in the power grid, not just in your GPS, but in all these sectors because of this interconnected system of our technological infrastructures that we use. The bottom line of it all is asking, what is the financial impact? Well, the financial impact is really hard to get to. One way that we did this by saying, well, we actually have information on insurance claims. We can look at insurance claims and we can correlate insurance claims with the strength of the geomagnetic variability on the day that the claim was received. This is insurance claims for industrial, electrical and electronic equipment. So this is not the cell phone in your pocket, but an industrial cooling plant or an industrial heating system or the IT system. And we found that something like 5% of all insurance claims had something to do with geomagnetic variability. On strong geomagnetically active days, the top 5%, that number increased to 20%. Now you might say that's not all that much, but there are two buts to this. First is, the Electric Power Research Institute estimated the total impact on society of all the power quality variations to be somewhere between $100 and $200 billion a year in year 2000 dollars. So you can double that more or less. Out of that, we take 5%. We're still talking about $5 to $10 billion a year. That is at least significantly more than what we're spending on trying to understand space weather. The more important thing, I think, is this. This shows there is ongoing impact of space weather. It's not like we have to wait for the century event for something major and potentially catastrophic to happen, but it happens already, and we can work on protecting our systems from their impact. Secondly, if you're talking about a century event, it typically means you haven't seen it yet, so we are speculating about its potential impact. This kind of study at least provides us a stepping stone that we don't go from never happened to potential impact, but the intermediate step of saying there are impacts, and we can now start doing system studies about what causes these impacts and how to prevent them and how to forecast the systems under which they happen. And then of course there's the pure intellectual interest in it. On the right-hand side, I'm showing you a visualization of all the planetary systems that we have substantial knowledge of the planets, and of course there are by now we expect something like several billion in the galaxy. But it means that there are many other places in which space weather happens. And it's interesting to think about how we can apply our knowledge from here to those systems. But maybe more importantly, we can then use those other systems to learn more about our own. We can learn about what happens in the heliosphere on a million-year timescale by looking at 10 years at 100,000 stars. And these are technologically feasible. They are being done, have been done. And then the final question here, before I go to the roadmap, is, well, how bad could it get? Well, that how bad can it get really has to come from archives that go well beyond the time scale that we've been looking at it, the 50 years that we've actually been measuring space weather by having instrumentation in space and susceptible infrastructure to that kind of space weather. If we look at sun-like stars, the Kepler mission is one of the inputs that we've taken from this. We can see that there are stars that, as far as we can tell, they're like the sun, solar age, solar rotation period, solar activity level, except for the fact that they flare at times with energies that are 100 to 300 times stronger than the largest solar flare we've seen in the last half century. We can look at radionuclides hiding in ice cores in the biosphere in your bodies. We can look at radionuclides that come from lunar rocks brought back in the Apollo era. Out of that we learn that even energetic particle storms can be more significant, more intense than what we've seen in the last half century, by maybe a factor of 3 or so, even on a million-year time scale. So maybe they saturate. Maybe there's something different about the sun. Geomagnetic storms are really tough. They don't leave records. So all we can learn is from the 150 years or so that there are direct measurements of geomagnetic variability. Except that we've learned just 2 years ago that we don't have to wait for another 150 years for the 150-year storm to occur. The Carrington-like strength event passed by the stereo spacecraft just 2 years ago. And the only reason we didn't sense it here on Earth is that stereo wasn't where the Earth was. That particular blast went off in a direction that the Earth wasn't in. But clearly these events do happen, and they happen more frequently than we might have thought. And the bottom line of all of this is each one of these aspects says it can get worse. And on top of that, or underneath that, we're building infrastructure that becomes increasingly susceptible. So it's really important that we know about space weather and that we protect ourselves from space weather.